It began like many astronomical discoveries, with a subtle alert from a telescope scanning the distant skies. But what followed would leave astronomers across the globe puzzled and exhilarated. A gamma-ray burst, among the most powerful explosions known in the universe, had been detected. At first glance, it was just another GRB, as they are known in the astronomical community. Designated GRB 250702b, it was initially flagged as a standard event, localized somewhere in the direction of the galactic plane. But this one wasn't standard. Rather than fading in a matter of seconds or minutes, GRB 250702b remained active for nearly 24 hours, a full day of cosmic fury. This singular behavior immediately challenged the conventional models of gamma-ray bursts, which are typically categorized into short and long events, lasting up to several minutes at most. Never before, in over 5 decades of gamma-ray burst observations, had scientists recorded a GRB that pulsed for such an extended time. And it wasn't just the duration that set it apart. The burst featured intermittent pulsing, with radiation surging and waning in a pattern that no currently known model could adequately explain. It was as if the event itself was breathing a cosmic lighthouse, flashing across the dark sea of space. As data poured in, it became evident that this was not an ordinary celestial occurrence. Gamma-ray bursts are catastrophic phenomena. They are often born from the collapse of massive stars or the violent merger of compact objects like neutron stars or black holes. These events are so intense that they briefly outshine entire galaxies in gamma radiation. Yet even among this rare class of high-energy emissions, GRB 250702b was special. What made this discovery even more intriguing was its origin. Using the Very Large Telescope, VLT, at the European Southern Observatory in Chile, researchers attempted to triangulate the exact source. At first, some suspected it originated from within our own galaxy. But further observations, aided by Hubble Space Telescope imaging, revealed that the burst had originated far beyond the Milky Way in a distant extragalactic source. This meant one critical thing. The energy levels involved were astronomically higher than if it had occurred locally. At a distance of several billion light-years, for this event to be visible at all implies that its intrinsic brightness was unimaginably powerful. To shine across that vast gulf of space and still be detectable by Earth-based instruments is akin to seeing the flicker of a match across a continent, except, in this case, the match is billions of times brighter than the sunday. The implications are staggering. Had such a burst occurred closer, say, within the Milky Way, it could have had devastating consequences for life on Earth. Gamma-ray bursts are capable of stripping planetary atmospheres and triggering mass extinctions. Fortunately, this one was safely distant, and instead of harm, it brought questions. The light we are now seeing left its source billions of years ago, during an era when Earth may have still been teeming with simple microbial life. It has traveled across expanding space-time, its message unchanged, until it finally collided with the mirrors and detectors of human instruments. In the span of a day, astronomers found themselves confronted with something rare, a burst that not only defied duration expectations, but also revealed an uncharacteristically variable brightness profile, suggesting either a sustained energy source or a series of repeated explosive events, something not previously observed in gamma-ray phenomena. It wasn't long before researchers began formulating theories. Could this be the result of a white dwarf star being shredded by an intermediate mass black hole? That scenario is as violent as it sounds. When a white dwarf, the dense remnant of a sun-like star, wanders too close to a black hole with thousands to hundreds of thousands of solar masses, tidal forces tear it apart. In the process, some of its matter is violently accelerated and compressed, releasing powerful bursts of energy, including gamma rays. Such black holes are rare, or at least rarely observed. Unlike stellar black holes or the supermassive ones at the centers of galaxies, intermediate mass black holes remain elusive. They've long been theorized, but direct evidence has been difficult to obtain. If GRB 250702b is the fingerprint of such an event, it could mark one of the first confirmed detections of this mysterious class of objects. Still, not everyone agrees on the white dwarf scenario. Alternative explanations include extreme stellar collapse mechanisms or even exotic forms of accretion, where matter spirals into a dense object in complex, previously unmodeled ways. These ideas are still under investigation, but the uniqueness of the burst means that many doors must be considered open for now. What's clear is this: we may be witnessing a new category of cosmic event. The event's host galaxy, faint, distant, and billions of light-years away, is still being studied. Researchers aim to determine the redshift of the source, a key value that reveals its distance and the era in which it occurred. Instruments like the X-shooter on the VLT and even the James Webb Space Telescope are being brought to bear, scanning the afterglow, looking for remnants or traces clues that might explain the mechanism behind the burst. It will take time, but one thing is certain: this isn't something astronomers see every day. What else is waiting to be discovered in the darkness beyond our skies? In the vast archives of gamma-ray burst data, few patterns hold more consistently than the brevity of these events. The universe has taught astronomers to expect two main classes of GRBs. Short-duration bursts, which last less than 2 seconds, are typically associated with the merger of compact objects, such as two neutron stars colliding and forming a black hole. On the other hand, long-duration bursts, usually stretching between 2 and 100 seconds, are linked to the core collapse of massive stars, a process that leads to a supernova. But what happens when a gamma-ray burst lasts, not seconds, but a full Earth day? That's precisely the challenge GRB 250702b presents. For over 24 hours, this cosmic eruption emitted intense gamma radiation, repeatedly spiking in strength. It did not fit the mold of any known event type. This wasn't a faint flicker at the edge of the visible universe. This was an ongoing, pulsing, high-energy phenomenon that could be tracked and reobserved, almost as if the universe had opened a window into one of its most extreme mechanisms and held it open, just long enough to demand our attention. This longevity has left researchers scrambling for an explanation. One possibility lies in what some astronomers refer to as engine-powered transients, where the burst is not simply the result of a single cataclysmic event, but is sustained by a central engine that keeps pumping out energy over an extended period. That engine could be a rapidly spinning magnetar, a type of neutron star with an extraordinarily strong magnetic field. Or it could be a newly formed black hole that continues to accrete matter in an unstable and energetic way. Yet, even these models struggle to explain the peculiar pulsed nature of the burst, not just sustained brightness, but repeated surges in energy over the course of a day. For this reason, GRB 250702b is not just long, it is anomalously variable. In astrophysical terms, this suggests a more complex origin than a single event. Perhaps there were multiple phases of disruption. Or perhaps the object that caused the burst fragmented in stages, feeding the explosion gradually. These patterns hint at a multi-step destruction, unlike the more instantaneous destruction observed in typical gamma-ray burst sources. Researchers have also speculated whether the event might resemble what are known as tidal disruption events, TDEs, catastrophic scenarios where a star gets too close to a black hole and is torn apart by its tidal forces. The result is often a slow, luminous flare that can last for weeks. However, TDEs are primarily seen in optical or X-ray wavelengths, not in gamma rays. If GRB 250702b was a TDE, it would have to be unusually fast, unusually energetic, and unusually intermittent, making it unlike any known example. Another possibility, a white dwarf star spiraling into a black hole, as mentioned previously. But this would require a black hole of intermediate mass, an object that, if confirmed, would help fill a major gap in the cosmic family tree of black holes. To understand this better, let's explore the idea. Black holes come in two primary flavors. Stellar mass black holes, which range from a few to dozens of solar masses, form from the death of massive stars. And at the opposite end of the scale, supermassive black holes weigh millions or even billions of solar masses and sit at the centers of galaxies. But between them lies a missing link. The intermediate mass black holes, thought to weigh between 100 and 100,000 times the mass of the Sunday, despite their predicted prevalence, direct evidence for such objects has been elusive. If GRB 250702b is indeed the result of a white dwarf being consumed by such a black hole, it would provide a crucial observational signature for this long-sought class. The process of tidal shredding, gradual fallback of stellar debris, and sustained accretion could, in theory, power the strange gamma-ray pulses we observed. Still, this hypothesis raises another problem: location. The host galaxy of the burst appears to be low in mass and not the kind of environment where large black holes typically reside. Unless intermediate mass black holes are more common in such places than currently believed, astronomers must look elsewhere for a complete explanation. And that has led to even bolder thinking. Could this burst represent an entirely new class of explosive event? Something never before seen and perhaps never even predicted? There is historical precedent for this kind of shift. In 1997, the first optical afterglow of a gamma-ray burst was discovered, transforming our understanding of GRBs from mysterious flashes to real, physical events located in distant galaxies. In 2004, a short GRB was for the first time linked to a neutron star merger, confirming that two different classes of events produced similar high-energy emission. Each of these breakthroughs came when an anomalous signal defied expectations. Each time, the universe was not random, it was revealing something we had not yet learned how to see. GRB 250702b may be just such a signal. For now, astronomers are watching not only to decode the event, but to prepare, because in the expanding universe of discovery, each anomaly is a clue that our models are incomplete. And sometimes, the rarest bursts of light are those that help us rewrite the books entirely. The next step is clear. Observe the afterglow, measure the redshift, map the host galaxy, and compare this strange event to every known phenomenon, searching for patterns or absences. The data are coming in, and they're not disappointing. What they mean, however, remains an open question. From Earth, the cosmos appears as a tranquil expanse of glittering stars. But telescopes remind us that space is anything but still. It is dynamic, violent, and ever-changing. And when something truly extraordinary occurs, like GRB 250702b, the entire global astronomical network mobilizes. The initial alert for the gamma-ray burst came through automated systems that monitor high-energy cosmic events. These systems, some onboard orbiting observatories, others on Earth flag unusual activity, and notify telescopes around the world. Within minutes, the alert for GRB 250702b had spread through the astrophysical community. Early detection pointed vaguely toward the plane of the Milky Way. For a moment, it was unclear whether this was a galactic or extragalactic event. This distinction matters. Bursts within our galaxy, though rare, are inherently different in scale and consequence than those that originate beyond it. It was the Very Large Telescope, VLT, at ESO, the European Southern Observatory, that helped clarify the picture. Using a powerful infrared camera known as Hawk-Eye, mounted on one of the VLT's 8.2-meter mirrors, astronomers observed a distant galaxy as the likely source of the burst. Soon after, Hubble's Space Telescope data confirmed it. The host galaxy was not part of the Milky Way, but lay far beyond a tiny smudge in the vast dark billions of light-years away. This alone reshaped the narrative. If GRB 250702b had occurred within our galaxy, the event would already be among the most energetic local phenomena ever recorded. But the fact that we could detect such a powerful signal from a galaxy so far away meant the actual energy output had to be astronomically higher, several orders of magnitude greater than previously imagined. In other words, we had not simply witnessed a large firework in our cosmic neighborhood. We had witnessed a thermonuclear warhead going off on the far side of the universe, and yet we could still see the light. To contextualize this, Light travels at approximately 300,000 kilometers per second. At that speed, it still takes over 8 minutes to reach Earth from the Sunday. From Proxima Centauri, our nearest neighboring star, it takes over 4 years. And from the galaxy believed to host GRB 250702b, it takes billions of years. This means the event we detected actually occurred billions of years in the past. The gamma rays we recorded had been hurtling through the vacuum of space since a time when Earth was teeming only with primitive microbial life, long before the emergence of complex animals or even multicellular organisms. This is the nature of deep-time astronomy. Every photon of light that reaches our detectors carries a message from the past. The farther it travels, the older the story it tells. Telescopes, then, are not just instruments of vision, they are time machines, revealing moments from epochs so distant they defy human comprehension. The host galaxy of GRB 250702b, as revealed in follow-up observations, appears dim, small, and relatively young. This makes it similar to the environments where many long-duration GRBs have been found in the past. Such galaxies often host massive, short-lived stars, the kind most likely to end their lives in catastrophic explosion. Yet in this case, the burst doesn't conform to known models. The variability, the length, the energy all point to something unusual. To better understand its distance and energy profile, astronomers turn to spectroscopy, the science of analyzing light, to decode the properties of its source. By examining the spectrum of the afterglow, researchers hope to calculate the redshift, a measurement of how much the light has been stretched by the expansion of the universe. The redshift value is key. It allows scientists to calculate the distance, the age, and the intrinsic luminosity of the event. It also helps characterize the galactic environment, including the presence of heavy elements, star formation rates, and even the possible mass of the host galaxy's central black hole. And here is where technology makes a difference. Instruments like X-Shooter, a spectrograph also mounted on the VLT, can observe objects across a wide range of wavelengths simultaneously, from ultraviolet through visible light to near-infrared. This allows for detailed mapping of the event's spectral features, even as it fades. Meanwhile, the James Webb Space Telescope, JWST, positioned far beyond Earth's atmosphere, can peer even deeper into the infrared. This is especially useful for observing ancient, high-redshift objects whose light has been stretched into longer wavelengths by the universe's expansion. Instruments across the globe and above it are now focused on the fading light of GRB 250702b. Observations continue, not just in gamma rays, but in X-rays, optical, infrared, and radio, each revealing a different aspect of the event. But there's more. If the burst was triggered by the destruction of a star, it's possible that a supernova occurred as well. These stellar explosions often follow or accompany long-duration gamma-ray bursts. Detecting such a supernova weeks after the initial burst would provide crucial confirmation about the type of progenitor involved. Alternatively, if the event originated from a white dwarf black hole interaction or some other exotic mechanism, the absence of a supernova might help rule out certain models. Every new data point refines our understanding. Every image, every spectrum, every light curve helps narrow down the possibilities. And yet, despite all this effort, the true nature of GRB 250702b remains unresolved for now. What makes this pursuit meaningful is not just the event itself, but what it represents. A reminder that the cosmos is far from fully understood, and that even with our most advanced tools, we are still early in our journey of exploration. Somewhere, in a faint galaxy billions of years ago, a force was unleashed powerful enough to travel across cosmic time and still stir our instruments into action. What could have been so violent, so persistent, and so strange? That's what scientists are determined to find out. Among the most compelling hypotheses to explain the exceptional behavior of GRB 250702b is a scenario both violent and rare, a white dwarf star being torn apart by an intermediate mass black hole. White dwarfs are the dense, cooling remnants left behind after sun-like stars exhaust their nuclear fuel. roughly the size of Earth, yet with masses comparable to the Sun, they are compact and stable unless something catastrophic disrupts them. Black holes, on the other hand, are infamous for their gravitational power. While stellar mass black holes are common end products of massive stars and supermassive black holes anchor the centers of galaxies, the intermediate mass black hole ranging from 100 to 100,000 solar masses remains a missing link in the cosmic hierarchy. Rarely observed and poorly understood, they are the ghost category in black hole astrophysics. But if they exist, they should be able to tidally disrupt a white dwarf, shredding it apart, much like a spaghetti noodle pulled tight. This event, sometimes called a tidal disruption event, TDE, can unleash immense energy. In the case of GRB 250702b, some astrophysicists believe that we may have witnessed such a rare cosmic death. A white dwarf, perhaps on a destabilized orbit, wandered too close to a lurking intermediate mass black hole, triggering a violent accretion sequence. As the star's material spiraled inward, it released powerful radiation, including gamma rays, the highest energy form of electromagnetic radiation. This would explain the longevity of the burst, with energy being released over time, not just in a single flash. It may also account for the pulsed variability, as the shredded material fed the black hole intermittently, like a dying heartbeat echoing across the universe. The problem is, we've never seen this exact combination before. While TDEs have been observed in the optical and X-ray spectra, typically lasting weeks or even months, they have not previously been linked to strong gamma-ray emissions. If GRB 250702b is truly a TDE involving a white dwarf, it could be the first of its kind to manifest in gamma rays. A discovery like this would force a significant revision of what we believe such events can produce. Still, as always in science, one explanation must compete with others. An alternate theory suggests an exotic form of stellar collapse, perhaps a rapidly rotating massive star with unusual magnetic properties collapsed in such a way that its core didn't immediately form a black hole, but instead spun down in stages, releasing energy over time. This scenario could, in principle, generate a longer and more variable burst profile than standard gamma-ray bursts. A third model involves a magnetar, a hypermagnetized neutron star formed during a violent supernova, which continues to release energy as it spins down. In some cases, magnetars have been observed to emit persistent X-ray and gamma-ray flares over extended periods. Could GRB 250702b be the signature of a particularly massive and unstable magnetar? Perhaps, though the energies involved may exceed even what such an object can deliver. Then there is the more radical possibility that we are witnessing something entirely new. It wouldn't be the first time. Astronomical history is full of moments when one anomalous observation changed the landscape of theory. The discovery of pulsars in the 1960 seconds was first interpreted by some scientists as artificial signals, the infamous LGM-1 or Little Green Men hypothesis, until natural explanations were confirmed. The first fast radio bursts, FRBs, baffled researchers for years. Even now, they continue to raise more questions than they answer. GRB 250702b may fall into the same category, a cosmic enigma that refuses to conform to established models. But before proposing entirely new physics, scientists must exhaust conventional possibilities. For this reason, much effort is now being directed at identifying the host galaxy more precisely. If it is truly billions of light years away, as suspected, and if its mass and environment are confirmed, this would constrain what kind of objects could exist there and what kind of event could have occurred. Measuring the redshift of the afterglow is key. This not only confirms distance, but also allows for calculation of the intrinsic luminosity, the total energy output of the event. If the numbers match what's expected from a tidal disruption, the white dwarf black hole model gains traction. If not, alternatives must be considered. Another critical line of inquiry is the presence or absence of a supernova. In many long-duration gamma-ray bursts, a supernova follows the initial burst, usually detectable in optical wavelengths days or weeks later. If no supernova is found accompanying GRB 250702b, this would suggest that the source was not a collapsing star, but rather something else, such as a disrupted white dwarf or even an exotic accretion event. And so, telescopes continue to watch. They measure, analyze, and wait, watching the afterglow fade with time, hoping for one last fingerprint to emerge. That final clue could tip the balance between theories, or open the door to a theory no one has yet considered. It is a moment of suspense in cosmic research, a moment when the data are real, but the explanations remain elusive, when hypotheses rise and fall with each observation. What we are left with for now is a puzzle, a long-duration, pulsing gamma-ray burst, visible across billions of light-years, originating from a galaxy scarcely detectable even with our most advanced instruments, and possibly, just possibly, caused by an object we've never seen before. For over 5 decades, astronomers have catalogued gamma-ray bursts into neat categories: short bursts, long bursts, magnetar flares, and tidal disruptions. But GRB 250702b may be a sign that these classifications are incomplete. That nature, as always, is ahead of our assumptions. Its extended duration, pulsed emission, and unprecedented energy output challenge the very framework we use to understand high-energy astrophysics. If the burst does not fit within any known model, it raises a provocative possibility. Have we just observed the birth of a new class of cosmic explosions? This is not merely a rhetorical question. In the history of astrophysics, the recognition of new object classes, from pulsars to quasars to fast radio bursts, has always followed a familiar pattern: anomaly, skepticism, study, and eventually a new paradigm. We may be witnessing that process again with GRB 250702b. What would such a new class look like? To qualify as a new astrophysical phenomenon, GRB 250702b would need to meet certain criteria. It would need to display consistent features across multiple instances, not just one isolated burst. It would also require a theoretical framework that can explain the physical mechanism behind the observations. And most importantly, it would need to be observed again in some future event that shares its characteristics. Currently, GRB 250702b stands alone, but researchers are already reviewing archival data to search for similar patterns that might have gone unnoticed in the past. In this process, pattern recognition becomes crucial. Scientists are combing through light curves graphs, showing how the brightness of an event changes over time, looking for long-duration bursts with variability or unusual spectra. They're reanalyzing previous gamma-ray events that might have been dismissed as noise or misclassified as other types of flares. This retrospective analysis is a common approach in science. Often, the first detection of something new goes unrecognized until a later discovery brings it into focus. The original fast radio burst, FRB, for example, was found in 2007 inches data collected years earlier. It wasn't until 2013 that the astrophysical community began to recognize FRBs as a real and distinct class. The search for similar GRBs could follow a similar timeline. At the same time, theorists are working to reverse engineer the event. Given the data, they attempt to model the physical processes that could lead to such an energy release. This involves computational simulations of massive stellar collapses, white dwarf black hole interactions, and even speculative scenarios involving exotic forms of matter or physics beyond the standard model. One idea involves asymmetric accretion flows, where the shredded material from a disrupted star doesn't fall uniformly into a black hole, but instead spirals in waves, creating intermittent bursts of energy. Another model considers fragmented fallback, where chunks of stellar debris return to the black hole in stages, each triggering a pulse. These are not standard models. They are, by necessity, hypotheses stretched to accommodate the unknown. Some researchers propose even bolder theories. Could there be hybrid events, where multiple mechanisms are at work: a magnetar spin-down embedded in a stellar collapse, or a tidal disruption nested within a binary system? These ideas, while speculative, are grounded in known physics and are testable, at least in simulation. Still, there is caution. Science is a conservative process. It leans heavily on accumulated evidence. The declaration of a new class of anything is not made lightly. It takes time, replication, and scrutiny. And so, as telescopes continue to watch the fading echo of GRB 250702b, astronomers wait for the next one, because if the universe produced one of these, it may well produce another. And when it does, the astrophysical community will be ready. Meanwhile, this single burst has already made an impact. It has expanded the boundaries of what we believe gamma-ray bursts can be. It has forced theorists to revisit old models and invent new ones. It has prompted fresh searches through archival data and inspired a new line of questions about black holes, white dwarfs, and the fundamental limits of cosmic explosions. And perhaps most importantly, it has reminded the scientific community of its own limitations. For all our telescopes, simulations, and models, the universe still holds surprises phenomena that do not ask for permission to exist within our frameworks. There is a poetic irony in that. Our models are built from past observations, and yet it is the outliers, the improbable, the unexplained, that often lead to the deepest insights. As one researcher put it, we don't study gamma-ray bursts to confirm what we already know. We study them because sometimes they do something that rewrites the rules. GRB 250702b may be such a moment, not just a long burst, not just a powerful one, but a signal from the deep cosmos that our understanding is incomplete and that somewhere in the dark beyond, nature is still writing chapters we haven't yet read. Could there be more of these waiting to be found? And what else might they reveal about the structure and future of our universe? As the initial burst faded, astronomers entered the second phase of their investigation, the long, methodical process of watching the afterglow. In high-energy astrophysics, the afterglow of a gamma-ray burst is just as important as the burst itself. It offers a unique window into the physical environment surrounding the explosion, the mechanisms that powered it, and the cosmic distances involved. Shortly after the detection of GRB 250702b, observatories around the world shifted their focus toward the coordinates provided by early detection instruments. The goal: capture the residual light across multiple wavelengths before it faded beyond detectability. This is where observational astronomy becomes a race against time. While the gamma-ray burst itself lasted nearly a day, the optical and infrared afterglows often decay within hours or days. Missing this window means losing the chance to capture critical data. Every photon collected during this brief period could be the key to unlocking the mystery of the event's origin. Among the first to respond was the X-Shooter instrument on the Very Large Telescope, VLT. X-Shooter is one of the few spectrographs capable of capturing a wide swath of the electromagnetic spectrum from ultraviolet to near-infrared in a single exposure. This makes it ideal for observing transient events like GRBs, where light is rapidly fading and repeat observations are difficult. Spectroscopy provides what is essentially a chemical fingerprint of the afterglow. By splitting light into its component wavelengths, astronomers can identify specific elements, ionization states, and molecular signatures. These patterns tell researchers what kind of material surrounds the explosion, whether it's a dense star-forming region, an older galactic halo, or a near vacuum. But most critically, spectroscopy reveals redshift. Redshift is the stretching of light waves caused by the expansion of the universe. The more distant a galaxy is, the more its light is redshifted. By measuring how much the spectral lines have shifted from their normal positions, astronomers can calculate the exact distance to the source, and by extension, determine how long ago the event occurred. For GRB 250702b, the redshift measurement confirmed what the Hubble imaging had hinted at. This event did not happen recently, and it did not happen nearby. It occurred in a galaxy billions of light years away, during an era when the universe was still relatively young. That revelation instantly elevated the event to one of the most energetically significant ever recorded. To shine so brightly from so far, GRB 250702b had to release an amount of energy equivalent to hundreds of millions of suns burning for an entire year, all in a single astronomical moment. The next major observatory to engage was the James Webb Space Telescope, JWST. Although designed primarily for infrared observations of the early universe, Webb is exceptionally well suited for studying distant GRB afterglows. Its sensitivity in the infrared allows it to detect cooler, fainter signals that Earth-based telescopes may miss due to atmospheric interference. Webb's instruments began scanning the host galaxy, searching for signs of stellar disruption, residual dust, and post-burst thermal emission. These observations are ongoing and may continue for months, especially if the host galaxy shows delayed flaring or supernova-like behavior. Meanwhile, radio observatories such as ALMA in Chile and Meerkat in South Africa have joined the effort. While gamma-ray and optical emissions fade quickly, radio signals from GRBs can persist for weeks or even months, providing another opportunity to gather data about the jet structure, environmental density, and shock interactions. This global, multi-wavelength campaign is part of what makes modern astronomy so powerful. No longer is the sky watched by isolated instruments operating in different regimes. Instead, networks of observatories spanning continents and orbital platforms collaborate in real time, creating a full-spectrum portrait of cosmic events from their earliest flash to their final whisper. This coordination is essential for piecing together complex events like GRB 250702b. For instance, if the burst was caused by a tidal disruption of a white dwarf, one might expect to see lingering infrared dust emission from the disintegrated star or X-ray flares from fallback accretion. If it was a magnetar, its decay curve might show periodic oscillations or a distinct thermal profile. Each potential mechanism leaves a different signature across the electromagnetic spectrum, and each must be ruled in or out with data. There is also the matter of searching for a supernova. Many long-duration GRBs are accompanied by Type IC supernovae explosions resulting from the collapse of a massive star stripped of its outer hydrogen and helium layers. If a supernova is detected in the host galaxy weeks after the GRB, it would strongly favor the collapsar model. If not, the weight of evidence may shift toward more exotic mechanisms. In this way, the fading glow of GRB 250702b becomes a test field for astrophysical theory, where simulations are matched against data and where hypotheses are shaped or discarded. It is a process that blends observation and inference, technology and theory, curiosity and caution. And even as the light fades, the excitement remains. Because what's being constructed here, quietly, methodically, one data point at a time, is not just an explanation of a single event. It is a new chapter in the story of cosmic violence. A deeper understanding of how stars die, how black holes feed, and how energy moves across the universe. Above all, it is a reminder that in the vast silence of space, even fading light can speak volume. The deeper we look into space, the further we see back in time. It's a phrase often repeated in astronomy, but it takes on a sharper meaning when an event like GRB 250702b appears. What astronomers observed on Earth, a violent, day-long burst of gamma radiation, was not happening in real time. It was not even recent by human standards. This light had been traveling across the universe for billions of years, only reaching our detectors now. That journey, measured not in kilometers but in epochs, began long before humans existed, perhaps even before Earth's continents had fully formed. The gamma-ray burst originated at a time when the universe was a very different place, denser, hotter, and filled with young galaxies still forging their stars. The light we see now is ancient, and yet its impact is immediate. This is the paradox at the heart of modern cosmology. In studying the most energetic events in the universe, we are never observing what is, only what was cosmic explosions echoing from a past so distant it borders on the abstract. But that past becomes tangible when its photons strike a detector. Every instrument that observed GRB 250702b from space-based observatories to ground-based telescopes recorded signals that had traveled unimpeded through intergalactic space. These photons crossed vast voids where galaxies are separated by millions of light years, where magnetic fields are faint and matter is sparse. And yet they arrived perfectly aligned, still coherent enough to tell a story. This is one of the extraordinary realities of astronomy. It relies on ancient messengers, photons, that left their origin before our species existed, before our planet was habitable, before the sun itself had ignited. And GRB 250702b tells us not only about its moment of birth, but about the medium it traveled through. On their journey to Earth, high-energy photons interact with intergalactic dust, cosmic microwave background radiation, and intervening galaxies. The way they arrive, how much they are absorbed, scattered, or redshifted, gives clues about everything they passed along the way. This means that one gamma-ray burst can teach us about the evolution of stars, the formation of black holes, the structure of distant galaxies, the expansion of the universe, and the conditions of intergalactic space. It is a cascade of information bundled into a few moments of radiation. But perhaps the most awe-inspiring aspect is that it reminds us how fragile and how powerful our observational window really island. The human species, with its relatively short existence, has only recently developed the tools to detect such phenomena. Until the last few decades, an event like GRB 250702b would have come and gone, invisible and unnoticed. The universe, exploding in the distance, would have whispered into silence. Now we can hear it. Now we can measure it. Now we can question it. And we do so knowing that what we are observing is not just a distant explosion, but a profound time capsule, a piece of the universe's memory, arriving just as we became capable of understanding it. There is a kind of poetic alignment in this. The event happened billions of years ago. The light began its journey across the universe long before humans walked upright, before mammals evolved, before oxygen filled Earth's atmosphere. And it reached us precisely in a moment when we had built instruments sensitive enough to recognize its signal and minds curious enough to wonder what it meant. In that sense, GRB 250702b is a meeting point not of space and time, but of cosmic event and conscious observer. It challenges our understanding of physics, yes, but it also challenges our understanding of scale, of patience, and of cosmic timing. It speaks to the rare alignment between what happens in the universe and our fleeting window to witness it. And it reinforces a core truth in astronomy, that everything we see in space is a relic. We don't observe stars as they are. We see them as they were. The farther we look, the deeper into time we go. In that sense, GRB 250702b is not just an astronomical event. It is a lesson in temporality. It reminds us that we live in a universe where time is not fixed, but layered, where the present is always receiving the past, and where even the most ancient light can change what we think we know today. And this light, violent, powerful, persistent, has changed something. It has made us look again, rethink again, and ask what else might be coming, from the edge of time into the lenses of our telescopes. Because if we can see this, what else might we still be missing? Astronomy often transports us to vast, incomprehensible distances. It pulls us billions of years into the past and stretches our imaginations to include exotic black holes and star death on galactic scales. But sometimes, the mystery comes from closer to home. Just as astronomers were grappling with the implications of GRB 250702b, attention was drawn to a very different kind of phenomenon, not deep space, but within Earth's own skies. A video had begun circulating. Captured by a thermal imaging system, it appeared to show a flying object, small, fast, and unidentifiable, being struck mid-air by a missile. The footage, presented during a public hearing by U.S. officials, sparked immediate speculation. The object appeared to emit heat, glowed white-hot on infrared sensors, and moved in a way that many viewers described as unnatural or even deliberate. Some speculated it was a drone, others said balloon, and still others raise the word UFO, or in modern terminology, UAP, unidentified aerial phenomenon. In many ways, this moment reflected a stark contrast to the distant grandeur of gamma-ray astronomy. Where GRBs come from billions of light-years away, this object was only kilometers above ground. And yet, the sense of mystery of something unexplained was the same. Scientific inquiry, whether it deals with cosmic gamma rays or flying objects caught on camera, must begin from the same principles. Observe carefully, eliminate assumptions, test hypotheses, and always account for context. One of the first to analyze the video was Michael West, a well-known astrophysicist and science communicator. His review was measured but clear. In his opinion, the object was not anomalous. He pointed out several key facts. The location where the video was recorded, a region in the Middle East, is known for active military testing, including ballistic missile defense exercises. Many of these exercises involve test balloons or drones, used as decoys or targets for interception systems. The thermal signature shown in the video, a hot interior and a cooler exterior, is exactly what would be expected from a balloon filled with heated air or a small drone with a warm core and thin outer skin. The apparent anomalous behavior, such as a change in speed or direction, could be explained by camera angle, parallax effects, or post-impact motion. Another voice in the analysis was Avi Loeb, astrophysicist and director of the Galileo project. Known for his open-minded approach to the search for extraterrestrial technology, Loeb also took a grounded view in this case. While not dismissing possibilities outright, he emphasized that the object's kinematics, mass, and size were consistent with known technologies, such as target drones used in military exercises. According to his assessment, the missile strike, which did not result in an explosive detonation, may have glanced the object rather than striking it directly. This too is consistent with known missile defense testing protocols, where warheads may be inert or configured not to detonate on impact. Together, their interpretations present a key message. Not everything that looks mysterious is unexplainable. Still, there is a reason why such videos draw so much attention. They occupy a liminal space in public understanding, where science meets perception, where classified activities meet public transparency, and where the desire for answers meets the limits of available data. And just as with GRB 250702b, the process of understanding these events involves multiple layers of inquiry. What is the source of the data? What are the properties of the object? What contextual information is available, historical, geographical, technical? What does the evidence rule out and what does it leave open? These are the same questions astrophysicists ask about any new phenomenon, whether it's a gamma-ray burst in a distant galaxy or a fast-moving object in Earth's atmosphere. But there's one key difference. In astrophysics, nature is usually indifferent to our presence. GRBs don't happen for our benefit. They don't respond to observation. They don't change when watched. Objects in Earth's skies, however, are part of a more complex system, one that includes human technology, military secrecy, sensor limitations, and public interpretation. This adds noise to the data, but it also adds urgency, because if something is flying near Earth, the consequences are more immediate than distant radiation pulses. And yet, the scientific approach must be the same. It requires clarity, precision, a healthy skepticism, neither too dismissive nor too credulous. It means accepting that unidentified does not mean alien, and that mystery is not evidence. It is a prompt to investigate further. And so, as the gamma-ray afterglow fades in the far reaches of space, and as infrared footage loops through internet debates, the scientific community is doing what it has always done, comparing data, testing explanations, and slowly replacing speculation with understanding. Sometimes, the greatest challenge in science is not answering questions, it's knowing which mysteries are real and which are only unfamiliar. Both require the same discipline. Both demand the same curiosity. And both whether from galaxies billions of light years away or skies just above our heads remind us that the universe still holds more questions than we have answers for.